Hello students, welcome back to the Unit 5 notes, section 7.3 this time. The warm-up I already did, feel free to pause here, but this warm-up involves bringing back our congruence because we're going to branch off away from congruence into similarity postulates. So remember, just like when we did congruence, we did not need all 6 pieces of the congruence statement to prove triangles congruent. We needed 3 sides, like side, 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 angle, side, where angles were included, angle, side, angle, where 2 sides were included between the angles. We also had angle, angle, side, and the HL theorem. Well, for triangle similarity, the same thing happens. We don't need all of the pieces. We only need a couple. And with that, we are able to conclude that they are similar. There's a lot less theorems. There's only 3. The first one is the angle-angle similarity. Think about it. If two angles are congruent, if 2 sets of angles are congruent, then the third angles are also congruent. Therefore, you have 3 congruent angles to 3 congruent angles, and that means that it's a dilation, that the triangle is a dilation of one another. So we have similar triangles when we have 2 congruent angles. We also could have similar triangles if we have side, angle, side. So think about this. We have 2 angles congruent to one another, and then we also have side AB proportional to side CD. Well, in this case, think about A as being a whole side, so RS. But yeah, so if we have 2 congruent, if we have 2 sets of proportional sides and the angle in between them is congruent, then it works out. And the last one is side, side, side similarity. So if we have 3 sets of sides proportional in ratio to 3 other sets of sides, then we also have enough information to determine that they are similar triangles. We're going to do examples of all of this. What's important to know is that you're using your these right here, the similarity symbols, because we are talking similarity. We are not talking congruence for the overall triangle similarity theorem that we're using. We also want to make sure that we have an included angle for the side angle side one. So let's dive into a bunch of problems that involve this. Again, here are your theorems all together. That's an example of angle-angle. Think about it. Angle S would have to be congruent to angle M. So you have 3 congruent angles in each. But again, you only need 2 of them. Notice the similarity statement as well. Side, angle, side. You have that angle caught in between. It's congruent. You have the 2 sides on either side of that angle, and they're proportional. Or side, 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 all sets of them are proportional. So let's get into the actual practice problems. Here in example 1, we're going to use the AA postulate. So here we have an angle, A. Here we have 2 angles. Here, by the vertical angle theorem, we also have another set of angles. So what I'm going to state here is that angle R is congruent to angle V, and angle, let's call it WSR. Notice I'm starting at where there's nothing, and I'm wrapping around and ending at 45. So I'm going to do the same thing on the other side. I'm going to start at nothing, angle B here. So angle BSV. So we have 2 congruent angles. And so what we're going to do is we're going to say by the side angle side theorem, we're going to say triangle WSR is similar to triangle BSV by the angle similarity postulate. And that is it. We are done with this one. In example 1, you have enough information to write a similarity statement, but do we have enough to find the similarity ratio? We don't see any side lengths, so there's no value to its sides yet. We don't know what it is, so we're going to say we do not have enough info to determine uh, the similarity ratios. Ratios, because we do not have any side lengths. All right, next one, example 2. Here we have QRP and triangle XYZ. It says explain why the triangles must be similar and write a similarity statement. Well, right now it looks like we only have one pair of angles, so I'm going to say angle R is congruent to angle Y. And then I'm going to test to see if my sides, so my question is QR proportional with XY as RP is proportional with YZ? So let's take a look. What I'm thinking here is maybe I can prove this by side, angle, side, and side, angle, side. So I'm testing to see if these are proportional. So I want to know, is QR proportional to XY as is RP and YZ? Because I already know the angles are the same. So I'm going to test its value. So I'm going to say 3 is to 4 as 6 is to 8. And what do you know? 3 over 4 equals 3 over 4. So not only do I know that these angles are congruent, but I also know that we have 2 pairs of proportional sides. So I'm going to make the statement that triangle QRP is similar to triangle XYZ. And I'm going to move some of this around. So I'm going to say triangle similarity. QRP is similar to triangle by the side angle side similarity. Now it didn't ask me what the, let me redo this. My apologies. So it didn't ask us the similarity ratio, but we already have it. We already know that the similarity ratio is, we know the similarity ratio is 3 to 4 because that's something we found earlier, which is right here in orange. So that's the similarity ratio, if it wanted to know what it was. All right, the next one, the next number 2, explain why the triangles must be similar. Write a triangle similarity statement. Well, we have no angles, and which means that we can't use angle angle and we can't use side angle side, but we can use side 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 similarity. So we are going to this is unique. Look at these sixes and these eights. So because we have two sixes and two eights, we really don't need to worry too much about our order. We do have to go in an order, but let's just this is up to how we want to do this. So I'm going to start with the largest ones. I'm going to go 9 and 12. So I'm going to look at 9 and 12. And I'm going to look at, let's say, 6 and 8. So I'm going clockwise here. So 6 and 8. And I'm going to look at 6 and 8 again. And again, I'm going down the longer side, then wrapping around the shorter sides. So it looks like if I divide both these by 3, I have 3/4. Divide both these by 2, I have 3/4. Divide both these by 2, I have 3/4. And yeah, that's proportional. Now we just need to write our statement. So we're going to say that triangle ABC, look at the order I went in. I went down the side that was a length of 9, and now I'm wrapping around this way. So I did ABC. So what I have to do is I either have to start at E and go this way, or start at F and go this way. I have to incorporate the 12 first. But again, it doesn't matter because I have a lot of freedom to go in either direction because of the fact that 8 is equal to 8 and that 6 was equal to 6. But what I will do is I'll start at F and I will go in the direction of E and then G because I'm going to stick with going clockwise. Again, it doesn't really matter. We're going to say it's similar by the side, side, side similarity. And that is it for that one. All right, this next one, example 3. The triangles are similar. It tells us that, so we don't need to worry about side or angle angle or side 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 similarity. But what I do need to do is pay attention to order. Notice they give me no order, but they want me to find DE. So they want me to find this length, but they give me no order. Well, that's fine. I'm going to take this idea of side angle side and work with that. So those angles are included. That makes it easier for me to figure out how to set up my proportional fraction, my proportional ratios, I'm sorry. I'm going to stick to both sides of that angle and keep that angle included to see what my ratio looks like. So if I were to take the number 12 in this triangle, notice that 12 is a shorter distance than 16. So what I need to do is when I go over to the other triangle is take the smaller one, the 18, because again, that is also connected to the angle because the angle is included. So I'm going to take the two shorter ones, 12 and 18, and compare them to 16 and 24. I mean, I should get that they are proportional, right? So 12 divided by 6 is 2, 18 divided by 6 is 3, 16 divided by, let's see, 16, wait, what did I do? 16, I meant 24. My apologies. I think I said 24. Yeah, 16 is to 24. So 16 divided by 8 is 2. 24 divided by 8 is 3. So that's my similarity ratio right there. Now, you don't need to use the similarity ratio. I'm just trying to demonstrate that they are similar. But it's a little bit easier now that you've dwindled it down a little bit to be such a lesser number, 2 over 3. Can you compare it to 12 over 18? Yes. Can you compare it to 16 over 24? Yes. what I'm going to do is I'm just going to take my ratio 2 over 3 and say that that has to be equal to the smaller of the two, so 10, over the smaller of this one, dE, which is x. Notice I went from left to right, 12 to 18. I went left to right, 16 to 24. I went left to right, 10 and to x. Or in this case, I went smaller triangle to larger triangle. So 2x equals 30, so divide by 2, and x equals 15. So I'm going to say dE is equal to 15. And that's it for that one. Just make sure your order is the same. So 10 is to 15, as 12 is to 18, as 16 is to 24. This next one, find the value of x in the figure at the right. Looks like by angle, immediately I see two angles and two angles. So angle similarity, these are similar. So now I just need to find out the value of x. I'm going to take the number 6 and I'm going to say 6 is to x. Why did I take x and not 12? Well, take a look. 6 falls between, it is included between both angles, 1 tick mark and 2 tick marks. 6 falls in between them. It's included. So I did the same thing with x. 1 tick mark, 2 tick marks. It falls right in between both angles, making it included. And now look at where 8 is. 8, and look where 12 is. It's attached to one of the angles, but it's not attached to the two. So I'm going to put it in the appropriate places. I went left to right, left to right. So 6 is to x, as 8 on the left-hand side is to 12 on the right-hand side. So I get 8x equals 72. 6 times 12, yep, 72. Divide both by 8. So it looks like x is equal to 9. And that's it. All right, the next one. All right, so now we're starting this. We're going to focus a little bit on indirect measurement, and then we're going to be done with the notes. Why is indirect measurement so important? Well, think about the pyramids in Giza in Egypt, and there's no way to directly drill through the middle and find out how tall it is, right? There are indirect ways of measuring these pyramids. There's indirect ways of measuring the Eiffel Tower. So what we can do is we can compare it to the same triangle in the same moment in time. For instance, a person's height and a cactus's height in the same moment in time when the sun is above them, and the shadows that they measure. Well, take a look here. We have angles that are congruent. We also have angles formed by the sun that are congruent. So here, we have the angle similarity happening right in front of our eyes. So what we can do now is create a proportion and solve for what we're looking for. 6 is to x, so the height is to the height, as the length of the shadow is to the length of a shadow. So we're going to say 6 feet is to x feet, as 4 feet is to 9 feet. Again, I'm going height of person is to height of person, as length of shadow is the length of shadow, going left to right, left to right. So in this case, we have 4x. 9 times 6 is 54. So we're going to divide by 4. Let me just make sure I'm doing the math right. 9 times 6 is 54 divided by 4 is 13.5. So x equals 13.5 feet. So we're going to say the height of the cactus is 13.5 feet. And it makes sense to leave it in a decimal form. And take a look. The height of the person is a little bit longer by a third, the length of their shadow. The height of the cactus is also just a little bit longer than the length of the shadow. So the question always is, does it make sense? And in this case, it does. Here's another one. This is going to be our last problem. Here's an indirect way of measuring a geyser. I personally am not going to go up to a geyser and try to measure it with a tape measure. Depending on if it's a steam, a jet of steam, it could burn you and could also send you flying. So we're going to indirectly measure this. You take a few steps away and you place a mirror on the ground. Then you walk away from that mirror. And when you look in it, you create, doesn't matter how far you go, but you create this angle measure that's congruent. So not only is your height perpendicular to the ground, but you also have congruent visual angles formed by the mirror that are visual. So we're going to say this is congruent by the angle-angle similarity. So what I'm going to do is I'm going to take the height of the person, 6 feet, and I'm going to set that equal to the height of the geyser, x feet. And I'm going to set that equal to 7 feet, the length or distance away from the mirror the person is, and then the length or distance the geyser is away from the mirror. And this from here, we're going to find our cross products. So 7x equals 240, half of 6 is 3, 243. 6 times 40 and a half is 243, divided both by 7. So 243 divided by 7. X is approximately 34.71. We're going to leave it 7, 34.7 feet. So we're going to say the height of the geyser is about 34.7 feet. The height of the geyser, this is approximate, is approximately 34.7 feet tall. And that's just one example of indirect measure. Notice that the person's height is just a little bit short of the distance away from the mirror. So 6 is to 7. That's pretty close. Notice that 34.7 is also close to 40.5. So it makes sense that we would get something just a little bit short or shy of the 40.5 feet. All right. This was the end. This is the end of 7.3 notes. You can start your homework now, and I will see you for the next video.